Greetings everyone, my name is Charles Cheong with matrix number MA19135. So in this video, I'll be talking about the chapter 1 and chapter 2, which are the introduction and also the experimental setup. So in the introduction, I'll be talking about the theory of this experiment. So conduction, convection, and radiation are the three processes through which heat energy may be conveyed. The transport of energy by convection will be explored in the experiment. Convection is the thermal energy transfer between a solid and a moving fluid. Convection is controlled by two phenomena, which are the energy movement caused by the molecular vibrations and bulk fluid motion. Now, convection is classified into two types, which are the forced convection and also the free convection. When heat is transported by the circulation of fluids caused by the buoyancy from density changes caused by the heating, the process is referred as the free or natural convective heat transfer. If heat is conveyed by circulating fluid caused by an external device, like fan for example, the process is known as forced convective heat transfer. Now, the addition of extended surfaces increases the heat transfer rate from a surface to a fluid. When increasing the value of the surface's heat transfer coefficient or the temperature differential between the surface and the fluid is not achievable. Newton's law of cooling states that the rate of heat transfer from a surface to a fluid through convection is Q dot equals to AH/Tm, where A is the cross-section area, H is the heat transfer coefficient, Tm is the mean temperature.
My name is Muhammad Afizuddin bin Muhammad Razman, MA1915. Okay, I will continue for experiment setup. Okay, this is a schematic diagram, a schematic design for experiment setup. Okay, first, this airflow. This is probate sensor. This is heater. This is thermal anemometer. This is plate sensor. This is fan control. This heater control. Okay, next. Okay, for experiment setup. Okay, A is a fan, B is a air duct, C, D and H is a anemometer point, E is anemometer point 2, F is fine plate heater, finite plate heater, Q is a cylindrical plate heater, I is power regulator. This is a power regulator. Okay, this is a digital power meter. K is a on off switch. L is a fan speed regulator. M is on a fan on off switch. N is a digital handheld temperature probe and water. O is a digital handheld anemometer. P is a plate heater placement. Okay, thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Alif Kabir Usmani and my matric number is MA19197. I will continue the slide presentation with the experimental procedure. Okay, experiment 1 is the free convection, which is the procedure number 1 is the LS17004 FFC. Free and false convection apparatus was placed on the table. The adjustable leveling foot is necessary. Okay, the next one is the 3-pin plug was plugged to the 240 VAC main power supply and the power supply was turned on. And the third one is the power supply unit K in front of the control panel was switched on. Next is the desired test specimen was selected and the shape of the selected test specimen was recorded. Okay, next is the test specimen was placed to the plate heater placement P and lock it with the wing nuts provided. Next is the test specimen heater cable was connected to the heater socket, which is located at the back of the control panel. And then the digital handheld temperature probe and meter was taken. The initial temperature TI in the air that was measured by putting the temperature probe into temperature point E. And then the temperature probe was placed to point D after reading the temperature at point E. Next is the power supply. The power supply was regulated to 50 watt by turning the power regulator I. Continue. Number 10 is the temperature TS2 was measured at point D for every 5 minutes, and then continued the experiment until steady state was achieved, which is where the temperature reading at point D became constant. And next is the experiment was repeated with other powers. And next is the experiment was repeated with the different types of test specimen. This is to ensure the previous heat plate is properly cooled before removing it. Next is the film temperature, which is TF, was calculated from the temperature result obtained. Then from the thermophysical properties of gases at atmospheric pressure table provided, all the relevant information was extracted out. And the number 15 is the volumetric thermal expansion coefficient beta, Rayleigh number, Nusselt number were calculated using the correct equation. And finally, the coefficient of convection heat transfer H was calculated, and hence the heat loss by convection Q using the correct equation. Okay, so for the experiment 2 is forced convection. Number 1 is the LS17004 FFC free and forced convection apparatus was placed on the table. Adjustable leveling foot is necessary. Next is the 3-pin plug was plugged to the 240 VAC main power supply, and the power supply was turned off. Then the power supply unit K in front of the control panel was switched on. Next is the desired test specimen was selected, and the shape of the selected test specimen was recorded. And number 5, if the test specimen was placed to the plate heater placement P, lock it with the wing nuts provided. The test specimen heater cable was connected to the heater socket, which is located at the back of the control panel. Number 7 is the digital handheld temperature probe and meter was taken. The initial temperature TI in the air duct was measured by putting the temperature probe into temperature point E. The next is the temperature probe was placed to point D after reading the temperature at point E. Number 9 is the fan switch was switched on, and the anemometer was placed to the point E. Then the fan speed was set up to 0.2 ms. The power supply was regulated to 100 watts by turning the power regulator, and the temperature TS2 was measured at point D for every 1 minute elapsed. And the experiment was continued until steady state was achieved, which is where the temperature reading at point D became constant. And yet next is the experiment was repeated with other powers, and the experiment was repeated with different types of test specimen. This to ensure that the previous heat is properly cooled before removing it. Next is from the temperature result obtained, the film temperature TF was calculated. Then the thermophysical properties of gases at atmospheric pressure table provided. Extract out all the relevant information for initial temperature, film temperature, and the temperature at point D when steady state. And lastly is Reynolds number, RE, Nusselt number, and heat transfer coefficient and overall heat transfer were calculated. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Mustaqim bin Mazuki. We'll continue our presentation for result and graph. So this is our experiment data for free convection. And this is our experiment data for forced convection. And next is graph temperature against time, which we get from these two data. So the first one is graph temperature against time for free convection, and the second graph is graph for temperature against time for forced convection. Next is calculation for mass flow rate. So for mass flow rate, we use equation M equal to rho AV, which is rho is density, A is area, and V is velocity. So for free convection, the the value of V and area is the same. So for 25 watt, we use rho equal to 1.1161 kilogram per meter cube. So we got M equal to 0.01765 kilogram per second. And for 50 watt, we use equal to 1.990 kilogram per meter cube. And we got M equal to 0.01738 kilogram per second. That's for free convection. And for forced convection, also we use velocity and area, the same velocity and area, but we use rho equal to 1.0089776 kilogram over meter cube, and we got M equal to 0.01595 kilogram per second. And the next is calculation for heat transfer rate. So for heat transfer rate, we use Q equal to H A multiplied by TS over T ambient. H here is enthalpy, or we can call it as temperature coefficient. A is area, and Ts is surface temperature, and T infinity is T ambient. So for both free convection and forced convection, we use the same equation. And for free convection, we got Q equal to 11.8501 watt. And for forced convection, we use and for forced convection, we get Q equal to 70.118. So for these two calculation, we use the same value of area and T ambient. The only different parameter is H and Ts. And lastly is the graph for heat transfer coefficient versus velocity. So from the graph, we can see if the velocity is increased, the heat transfer coefficient also increase. So I think that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Rizal bin Muhammad Fadli, MA19258. I will continue with discussion. Number one is version of heat transfer in free and forced convection modes. The process of transmitting heat via harsh motions of water droplets. The conductor is responsible for the initial heat transfer between the item and the liquid, but the fluid movement is responsible for the majority of the heat transmission. Natural convection and forced convection are the two types of convection. Natural convection is caused by varying densities in liquids owing to temperature variation. Next, difference between laminar and turbulent flow. Turbulent flow is erratic and chaotic, whereas laminar flow is smooth and streamlined. Laminar flow has a low Reynolds number, while turbulent has a high Reynolds number. The increase is in heat transfer rate in a turbulent flow environment is greater than in a laminar flow situation. Number three, it different in the measure value of heat transfer coefficient. To understand the difference in value of heat transfer coefficient based on two different method of mean temperature calculation, we need to understand how to depends of the temperature for free and forced convection heat transfer. After that, the effect convection mode on the efficiency. Since more fluid can travel across the system at the same time, more heat from the fluid may be released from the heat sources. Convection is a more efficient means to convert energy than energy in liquids like water and air, because the difference in performance result in a significant difference in the time it takes to melt the ice. Next, the effect of extended surface on the heat convection. Fins or extended surface are commonly exploited to increase the rate of convective heat transfer between an object and the surrounding water. Due to the enlarged cross-sectional area where the convection process occurs, extended surface or fins are exploited to promote heat transfer. The fins material should be thermally conductive with a temperature gradient from bottom to top that is adequate. P-inch fins, straight fins, ring fins, and other type of fins are available in a range of form and size. For the conclusion, in conclusion, it can be stated that in the case of natural heat convection, the convection heat transfer coefficient and the heat loss owing to convection, thus as the power supply increase. The temperature reduction owing to conduction and the convection heat transfer coefficient both rise. We may deduce from the graph that the temperature at the point D rises with time as the power supply rise. Furthermore, heat transfer is not possible at the length fin lengthening is not cost effective due to waste of material, greater bulk, additional weight, and expense. That's all from me. Thank you.